The whole talk here is more to engage you guys in a dialogue so that you can help me solve the future network architecture problem, because I really don't know how. So I'm going to talk about mostly what I see happening, some stuff I'm playing around with, but I think the good question, I will be having a lot of question answers and engagement. So I'm going to talk about three trends, which kind of we all know about: over-provisioning, exponentials, and a debate on centralized versus distributed. And then I'm going to talk about some stuff that is in what I call the ESN playground of technologies that we are playing with, and again see how that affects our future network architecture and what does that mean. So I'm going to start with over-provisioning. And I think I started working in networking around 10-15 years ago. It's been 20 years now. I lose track of time. And it was always one of the things that we were told in the internet is throw bandwidth at the problem, it'll get solved. Why do we need to build more technologies, more complex technologies? When we started talking about virtual circuits and bandwidth on demand, I think there is still a lot of people who say, why is it all needed? Why not do over-provisioning? So the question I want to talk about is, if you throw bandwidth to fix the problem, does it really work for the research and education traffic profile? And I think one of the things I want to point out to everyone, and I think it's reiterating, you've seen these slides before, is this graph. And this is a graph which kind of, we have been showing around a lot. It talks about moving data, using grid FTP or certain technologies across distances. So if you have a 10 gig link, and if you have absolutely zero packet loss, when you go from local to metro to regional to continental international, this is the profile of your throughput that you will get across the links. So you really get 90% of your link capacity as throughput. But if you even have 0.0046% packet loss, and that, to kind of make it real, it's one packet out of 22,000 packets if it falls on the floor. It's discarded. You can see how your performance goes up to 5% when you're trying to move data over continental distances or regional distances. And this is kind of round trip time in milliseconds, so 50 milliseconds, 60 milliseconds. You can see based on your country and what you're doing, how many millisecond delay it is. And this is measured, it is theoretical, both of the numbers match, and this is the profile you get. So even though you have put in a 10 gig line and you're paying for it, and your service provider puts in a 10 gig line, if there is packet loss, you're not going to make advantage of the bandwidth. So what that means is throughput is more important and not bandwidth. So throwing bandwidth at the problem usually doesn't solve for such kind of applications when you're trying to move large amounts of data. Now if you're doing web browsing, and there is a lot of web browsing happening, obviously, throwing bandwidth at the problem sometimes helps. And the other thing is, the throughput is an end-to-end problem. So if, as an R&D network provider, you throw a lot of bandwidth and you put 100 gig links in your backbone and you claim, hey, we have helped the applications, you haven't helped the applications. They're not going to be able to take advantage of the bandwidth you have in your network. So I think you have to stop thinking of bandwidth, you have to start thinking of throughput. And that's kind of really important. So I'm going to give you one more example. So you all know about elephant and mice flows. And elephant flows are the huge data flows, the 10 gig traffic that I talked about. And mice flows are your web browsing, you're fetching bits of data on your web page, or you're sending an email or something like that. That's called the mice traffic. It's short-lived small flows versus long-lived large flows. Now we did an experiment just in the lab. So this is not wide area network. This is just in the lab, back to back. And we went from one data source. We sent a whole bunch of concurrent small flows to reflect loads like browsing Yahoo, using Amazon, going to Facebook or reading the news. And on this end, we started an elephant flow. So let's talk about it. So we had 4 concurrent flows, 8 concurrent flows on a 10 gig optical circuit, and it's barely consuming 100 megabits per second, 150 megabits per second of traffic. So you would expect when you put an elephant flow in this 10 gig pipe, it will consume the rest. So you will get, you should get 9.8, 9.9 gigabits per second. It's back to back, no packet loss. You should get that. But over multiple experiments, what we saw, with different number of concurrent flows, from 4 to 64 concurrent flows, that we could not get effectively more than 5 to 6 gigabits per second of throughput for the elephant flow. So even though there is not a lot of bandwidth being taken by small flows, it interferes with the big flow and how much traffic you can get through. So we need to understand that, because now we have got 10 gig networks and you're putting big flows and small flows all in the same pipe. And how they interact is something that is not clear. So I think more work needs to be done. We have to engage in looking at long distances, 100 gig pipes. This is just a little bit of a hint on, there are microbursts that actually affect congestion and they cause large flow not to get the full bandwidth that it could get if there was no concurrent flow. So, we did run it without the concurrent flows and it would get around 9.8, 9.9 gigabits per second because these are well-tuned hosts. So that's something you have to think about when you think about over-provisioning bandwidth and how it affects throughput and your end applications. Now, another common thing that has been there that, hey, RNA networks are rich, they will always have excess bandwidth, they will always be over-provisioned. Why worry about things? RNA networks are these rich kits that play. But I want to talk to you about another trend, and it's called exponentials. This is actually a graph from ESNet from 1990 going all the way to 2014 January. And you can see how the traffic has been going exponentially. This is 15 petabytes a month data movement right now, and seemingly we are waiting for LHC run 2 where it will grow even further. So let's talk a little bit about exponentials. There are two things. One is, thankfully, exponentials cannot last forever. So they do go away, but they take a long time. So let me talk about Moore's law and what it means for network equipment. So Moore's law, people are saying it's on its deathbed around 2022 when they expect Moore's law not to hold anymore. The reason why it's an exponential is it's a transistors per chip, 2 to the power of E minus 1959 divided by 1.5. That's the Moore's law. That's what gives you the graph. Now, IBM mainframes went away when Moore's law took place because people could build PCs small enough, computers small enough. There were a lot of commodity computers. And right now we have the equivalent of multi-terabyte router platforms. But do you think they can scale up as your traffic grows up exponentially? Right now what they're doing is they're doing backplanes to put multiple of these routers together. Also, if you think about what happened to the IBM mainframe, now data centers have small commodity computers all networked with each other to really make a large computer. That's what Hadoop does. They don't need a big mainframe to do big calculations. How will it change the router platforms? Is it going to be a whole bunch of commodity layer 2 switches banded together to make a big router? Do you really need this big device? I'm not saying I have an answer, but that's one of the questions that I think we should ask. What is the future if Moore's law goes? What kind of architectures we need to think about? And I really conjecture that single platforms, or what we call God boxes, which is the big CRS routers, are going to be history because they're not going to be able to fit in the one rack energy density that you need, because the chips are not going to be doubling in transistor capacity after a certain time. So we have to acknowledge that and see what that means for our network architecture. The second thing I want to talk about is the Shannon limit. This is a graph from Peter Windsor, who's the head of optics research in AT&T Bell Labs, and I copied it from him. And this was given a year ago, so some of the data is old. But products in, I think, 2011, 2012 timeframe were around here. That's what your current WDM products are, which is around 2,000 kilometers, 100 gigs. That's what you guys get, 2,000 kilometers, 100 gigs. And if you looked at the WDM experiments, it was all over the map, depending on what spectral efficiency you need. So spectral efficiency, for people who don't know, is when you do DP-QPSK, you get 4 bits per hertz. It's about how do you modulate the signal to get more bits in the same spectrum. Now, if you look at it, to get around 400 gigs per second, it's around here. your distance is around 500, kilometers. So think about moving from 100 gig waves, 2000 kilometers to 400 gig waves at 500 kilometers. You need 3 more regions to get 400 gig waves. So not only is 400 gig waves more expensive, now you put 3 regions in it, so it's super expensive. So do you think that's a viable technology as you go long distance? And according to his projections, to really meet the traffic demand, which is 60% traffic growth per year in the internet, you really need this capacity, and that is beyond the Shannon limit. So there is something that has got to give. And this is 2015, I think the predictions are, maybe a couple of years here and there, but it is pretty accurate that to really, we need a huge amount of spectral efficiency, and it's just not happening right now. So that is, as we deal with exponentials, we have to realize that there are certain limits that we are close to hitting. Moore's law is one of them, optical spectral capacity is another. This is an article that I published with a few people recently. It's in September, Optics and Photonic News. I think it's worth a read. And I think there are some things we conjecture. These are 2 graphs from that article. One is, people talk about traffic growth is slowing. Our conjecture is it is because the optical capacity is actually limiting traffic growth. And that is one thing we need to think about, because the carriers are not deploying more and more because it costs more, there's a lot more re-engineering, and it's not easy to go to 400 gig right away. While the number of devices per person, the number of people who are using internet is growing truly at an exponential rate. So there are some strategies and some explorations, research areas in optical networks that we talk about. I'm not going to bore you with that, but that is something to think about. So what is the impact on the network architecture? So how do you architect a network to handle exponential growth? It's a big question that we all need to answer. What metrics do you collect so we know quickly when the exponent changes? Either it increases or decreases. So if the traffic is truly slowing down, it affects on how we build things and when we build things. And then what is the best architecture to reduce over-provisioning, because over-provisioning drives cost and is most affected by exponential. So one of the things I'm going to get into is this whole argument of centralized versus distributed, which has been been roaming the hallways since SDN has come into vogue. So let me opine on that for a little bit. So one of the questions is, who won the debate? And I don't know how many of you were in the 2011 Naughtynet conference in Reykjavik. There was a plenary talk by Kiriti Kampela on control plane distributed or centralized, and it was still a very much an open debate at that time. But I think right now, if you look at Google's learnings, and when they talk about engineering massive systems at scale, the conclusion is logical centralization of control with peer-to-peer data plane beats full decentralization. That's their conclusion, and I'm happy if you want to challenge it. This was actually given by Amin Wadad, and as something with examples too. So their data center design is fully decentralized with logical control, logical centralized control. Their Google file system, their MapReduce, Bigtable, and their B4 SDN network, which is a wide area SDN network. So there are multiple examples where logical centralization has beaten full decentralization in terms of efficiency, scale, manageability, and all those characteristics. So I would say that wins the debate, but in the sense, answer is neither full decentralization nor full centralization, but a little bit of both. So if I look at this decentralized to centralized and talk about traditional packet being decentralized, traditional transport being fully centralized, we think about PCE and all of that work going on, and IETF is moving it from decentralized towards centralized. We look at the Contrail, Lumage, and OpenFlow, it is more centralized than decentralized. And I do believe SDN is going to somehow move from the centralized angle to somewhere in between, and that is what's going to be the sweet spot. We don't know what that is, but I have some ideas that I would like to share with you on what this hybrid SDN approach looks like. So the way, when I think about hybrid SDN approach, I think the easy way to is to look at yourself in the human body. Most of the strategy on what you do and what you think is done centrally in your brain. And it's all service-driven, policy-driven, where there are decisions to be made. But when someone attacks you, or when you breathe, you really do it instinctively. It's not something that you are pushing up to the centralized controller and say, take the next breath. Take the next breath. You're not doing that. So I think all instinctive things should be done within the hardware. So what do I mean by that? ARC handling. Why move the ARC to central controller? No point doing that. Ping. You should be able to handle in the data plane and not send the ping packet as a packet into the central controller to handle. So there are things, restoration, protection, there are things that need to be done, and then more strategic things like traffic engineering, managing paths, managing traffic, making policy changes can be centralized. So this hybrid SDN approach is what I believe is going to work, and you know, people are going to find a medium. So even though you see a lot of these debates, I think the debates are really not worth happening. What we need to do is to find this balance ourselves. So the next I'm going to talk about, given all these things that we know, what is the playground that we are playing in? What are the things we are doing? And again, it's more to initiate a dialogue with you guys rather than say this is the right way to go. So the first thing we want to think is rethink capacity planning. It's driven by exponentials and over provisioning. How do we do capacity planning? This is actually the logarithmic chart of this hockey stick that we had seen before. And if you look at this hockey stick, I want to share something with you. So this is the traffic growth. This is zoomed into the last 5 years. And this represents our network bandwidth. So this is our over provisioning, if you look at it. And you know, you can see that you get to 30% capacity, you bump up, you add another wave, you know, you have more over provisioning, and you know, this cycle goes. Based on this traffic growth and this capacity, we did 3 projections, A, B, and C. A conjecture was, hey, there is more data coming, we're going to go faster than our historical growth. B was, 20 years of data, we're going to go at the same rate, why would we go any faster? C was, you know, we are slowing down, you know, how we cannot have an exponential go on any longer. So these were the 3 scenarios. Speed up, stay at the same rate, slow down. So when I look at what is the cost of A, B, and C of over provisioning, and this is assuming that upgrades are based on 40% traffic occupancy. This is numbers based on that. So this is the chart we came up with. So I'm going to walk you through this chart a little bit. So let's look at different metrics. What's there today and A, B, and C scenarios. Okay, 5 years out, and this is projection 5 years out. So let's look at number of 100 gig interfaces. We have 100 gig router network interfaces in our network today. That's what we have. So if we go lower than historical, we will add 100 more in 5 years. If we go same as historical, we'll be adding 200 more 100 gig interfaces over the next 5 years. But if we go greater than historical, we'll be adding 400 more interfaces over the next 5 years. So if you look at budget, what does it mean? This will require 14x the spending than what we spend today. Try growing your budget, especially on a government, 14x. Then you kind of start thinking why we need a future network architecture which is different. But not only that, colo and power. We need 55 racks for A, while just 11 for B. And our budget power in terms of cost will be adding $600,000 or $500,000 worth of just colo and power to handle this. And this is just in the last year. This is not aggregate. These are aggregate, but this is not. So if you look at this, you see that essentially C, if that is the case, we can survive. Business as usual, just keeping the same stuff, no need to change the network architecture, we're good. But if it is B, we need some revolutionary change in 5 years of our network architecture. Or if it is A, then we need it in 3 years. 3 years is kind of close, it's very uncomfortable. So that's kind of what led me to choose this topic. And Lars asked me, what are you going to talk about? Because, you know, depending on how it grows, we don't know. where we're going to go. So then the question comes, do we change the thumb rule of network capacity? Go ahead.
So how did you calculate the price? I mean, looking at our networks, we have been building networks for 20 years, and we have been able to upgrade them every time. And we have been doing that at the same price as the last network.
So he's asking how did you calculate the price? Traditionally, RME networks have been able to upgrade networks at the same price over the last 20 years. It's exponentials. So if you, I mean, I have this saying about rabbits, right? So if you multiply rabbits, you know, they have 2 rabbits get together, they have kids, they make 4 have, you know, once you look at exponentials, there is a time when that doesn't hold anymore. And this is based on current equipment prices, 10% decline in cost of gear, not assuming 400 gig gear at any price, it's just 100 gig gear at current prices, 10% decline every 5 years, and then doing based on traffic upgrades. I mean, these are all projections, of course, based on what we see the traffic growth. Based on the traffic growth, when we see 40% occupancy and we upgrade, the pricing, what we do, colo, is we do a 10% decline in equipment pricing year on year for both router interfaces and optical interfaces. And the colo power we see at growing in terms of power costs 3 to 5% year on year from here to the next 5 years. So these are the kind of metrics we used to come up with this network. Now we have a different network than yours. We have a larger footprint to provide a service on. It's US wide, which is a huge footprint, and it does. And we are operating our own fibers, which is what we are doing as well. But it will be good for you to do the study. Maybe your traffic is not growing at the rate as ours is.
We expect our prices to go down next year.
Okay, good. And that's why I'm here for a dialogue. What network architecture will bring the price down in the next generation? Go ahead. Oh, 5 minutes. I have actually more slides, so I'm going to take more time. Okay, so I think it's a race between over-provisioning and traffic growth, and I think the trade-off is smarter capacity utilization versus growing our budget. And I think this is kind of the goal, is to see if we can survive, which is the before SDN picture, at 100% rather than upgrading at every 40% capacity. So I would love to see your numbers, by the way, and see how you calculate that you'll be able to do the same thing. So next thing is science applications in tackling end-to-end throughput. So we have been talking about science DMZ, and it's kind of 3 things. It's friction-free network path, dedicated data transfer nodes to be able to take advantage of the network, and performance management to make sure we have no loss, because we saw what the impact of loss was. So these 3 things have been driving the science DMZ. It's a thing. But why is it important? First, because throughput is end-to-end. And if you don't solve the end-to-end, it does not matter how much network WAN capacity you have. They won't be able to make use of it. Your traffic won't grow, and maybe you won't come into the situation of needing a new network architecture. But we believe that our mission is to help enable science, and it's not about making a network work within the budget. So our goal is to help unstuck the end sites. And the way we can do that is by providing an abstraction, a structure to make traffic flows more predictable, manageable, and this kind of gives you a design pattern that we can deal. We know which traffic is high flows, large flows, because it's coming from the science DMZ, which are not. Right now it happens all over the place. We don't have any visibility into the campus. We can't manage it. So this better abstraction is what is happening, and I can just say that in US, these are the universities funded to deploy science DMCs. These are the last 2 years of CCNIE and CCIIE awardees. And from a US perspective, we are getting this unstuck. But after reading Renee's slides this morning, I'm wondering, why is this not all over the world? Why are the campuses in Europe not deploying science DMCs? Is it the NIH syndrome, or is it something else? But I think it is very important to have this deployment, because in Cliff, I think Eric knows this, we talked about campus networks and what the blocks were, and we talked about it and we couldn't solve that. So this is one of the ways we have gone about solving that, and we see that having a lot of traction. Okay, I'm going to speed up, sorry Lars. So again, the other thing what we have been doing is, there is a change in network technology, especially with SDN. So our approach there has been, The only way that you can get the industry to put the science requirements is by leading and doing some stuff that they will acknowledge and incorporate into their product designs. If you get ahead of them sufficiently, you can influence them. We did that when the internet was going, because a lot of internet technologies are based on HEPNet and MFENet and all these science networks. Now was a chance to do it again. So we have been experimenting on multi-layer networking. We did a demo with Brocade and Infinera. And I just want to kind of say that we showed that by automatically moving flows with SDN provisioning and multi-layer, we could really go from the 6 gigabits per second block that you see earlier and get the elephant flows, the full 9.9 or 10 gigabits of traffic. No.
So you see this spike in performance. Was that because of SDN or was that because of smart pathfinding?
I don't see the difference. SDN-based network figured the topology in the path and reconfigured the network without packet drop that allowed this thing to happen. So it's all interconnected. No, there's no packet loss. What I mean to say, it redirected the traffic, so it was not that you had to tear down and restart the traffic. It redirected the flows.
Well, right. So the question I have fundamentally is this because we did proper traffic engineering, proper pre-configured provisioning, or was it because we had this centralized software defined?
It was a combination of anything. It was detection, it was decision making, and it was reconfiguration. Now you can break it to your individual components, or you can say this whole area is software and it's part of the software-defined networking. Now, it's a debate, we can take it offline. But I think the thing I want to point out is that this got the Best Paper Award at Hot Interconnects this year. And that's what industry is seeing, and you're seeing a lot of what we're trying to do is to write papers and make this happen. The other thing we are investing in SDN is focus on operationalizing, and we see a lot of gap in SDN not being operationally ready to deploy, manageability, implementations that interoperate, and security. These are the 3 missing pieces. And you can read a lot more about what are the missing pieces in SDN in this report. That was a big, NSF DOE meeting in December last year, and there's a report on what the findings were, what the recommendations were. And one of the recommendations is actually implementing a software-defined exchange, which a lot of us have been working on. I'm going to skip what is a software-defined exchange, but I want to show you that one of the things we have been doing is investigating what a software-defined exchange is, and which is, in this case, a layer 3 exchange of building a router using a top-of-the-rack simple switch and running BGP out in the SDN controller. And right now we have BGP routes sharing with Rians and with South Sandron, and this system, you can see, this demo at Glyph. Whoever is going to Glyph next week, you will see this demo working there. And it's a multi-continent SDN BGP peering. We are hoping to add more people to this peering, so we can truly get an experience. What does it mean to run an SDN-based router, where BGP and BGP processing is up in software, and the hardware is a simple Ethernet switch? Can we make this work? What are the gotchas? What is missing? That's what we want to do, study with this work. And again, this is a lot of help from Google research that we're getting in terms of software that we've been leveraging. I'm going to briefly talk about named data networking. So when you talk about moving data intelligently, you don't want to keep moving the data over and over in the network again. So for that, we've been using named data networking. It's a collaboration with Christos Papadopoulos from Colorado State. And what we're focusing on is NDN for science, and how does it help science? And let's just say that we built a testbed over ESNet. This is what the testbed looks like, and this is research that grad students and climate researchers and we are doing to see what the value of named data networking is there for data and data movement. So conclusions, please. I think you've got the gist of my talk. All I can conclude is there is change ahead, and we've got to be prepared for that. And if there is any ideas, and I heard some comments, I'm happy to engage in a dialogue. Thank you. Sorry to have taken more time.
Thanks, Rodney, for an one pressing question we can take, but otherwise I know Inda will be here and you can chase him down and he will hopefully be able to defend himself.
Okay.
People will put you down in the lunch break. So thank you again. So, moving on, one of the things about innovation is that we have to do new technologies, but we also have to make sure that Linda talked about how we can operationalize those new technologies. And to operationalize them, we really have to look for standardization. And in various areas, we have to do it in protocol, we have to run into the standard budget. But once you do that, you face a challenge of making sure that the things that claim to be compliant with standard actually are compliant with standard. And partnerships, so one project that's doing that partnership is from Polish Emirates Pioneer, working with Boston Supercomputing Center. He's been working with us on different projects on next generation network, advancement of demand, provisioning systems, and so on and so forth.
Thank you very much for a warm introduction. My name is Bartosz Belter. I'm here on behalf of the whole team, NSI contest team. So we changed slightly the topic. Right now, I'm going to give you a bit of how to test platforms. So what is the NSI contest project? It stands for Network Services Interface Conformance Test Suite. So we aim in the project at building an NSI version 2.0 compliance test suite, and we plan to offer this to all developers, NSI bandwidth on demand developers as a service platform. This is one of the GEANT open call projects. We have been selected by the GEANT community to run this project. It's coordinated by PSNC, and we work together with an Italian SME, which provides a lot of expertise in software engineering and networking. So let me start this talk with a famous sentence from Dijkstra. Testing shows the presence, not the absence of bugs. So I'm pretty sure you are aware how important in the whole process of software development testing is. So even if we run extensive tests on our platform, we are not sure if we cover all the tests. There are several metrics which can help you to bring your software, let's say, more and more mature. I'm pretty sure there are software engineers in this room which know a lot about this thing. What I would like to show you is just a couple of examples of software disasters happened in the past, so this may also happen with networking. So testing is important. The first video shows, it's copied from YouTube. In fact, it shows Ariane 5. This is the European rocket project. It was destroyed just a couple of seconds after launch. So the cost, $500 million. It was caused by the conversion problem from 64 bits to 16 bits format. The fact is that this project, Ariane 5, the software was not properly tested. It was just adopted from the previous project, Ariane 4. So this cost $500 million, just this mistake. The second picture is even more tragic. So in 1991, the Gulf War, there was a Patriot missile system, which was designed to track, intercept, swoop missiles. So due to the problem of software rounding error, which properly calculated the time, a missile reached the target, and 28 killed, more than 100 people injured. So this is really tragic, and again, it's a software problem, not properly tested. And a bit of fun, this is just a news from Polish internet, a speeding ticket, September 2014. The car exceeds the allowed speed with 0 km/h. So here, the software failed, obviously, because the ticket was issued, but there was also a human intervention. So not only the software itself, but also we have problems with humans behind the software to raise this ticket against people. So we are not sure whether we can test properly the software or not. And coming to networking, bandwidth on demand is a mature technology. So nowadays we see bandwidth on demand used in several projects, run for radio telescopes. We also run these in local networks to provide network services to our communities. We had coordination of these efforts. There were partners really interested in developing stacks. And this led us towards a standardized interface, network services interface, created at the OGF working group. So now the question is how to efficiently test these independent implementations of the NSI protocol. At this moment, at least from my experience, I haven't seen the usage of such technologies, bandwidth on demand technologies, in such critical use cases as I presented before. But things are changing. So we have collaborative projects between different research centers. There are projects which will rely heavily on networking. So we need to make sure that all the platforms, all the networking features are properly tested. So now I'm coming to the clue of this talk. I'm going to give you a short overview of the NSI contest project. So the main objective of this project is to provide a framework for validation of the compliance with the standard, with the OGF working group standard. By a framework, I mean a set of tools which we will develop implementing the NSI conformance test suite. The suite will be compatible with version 2 of the protocol released some time ago, which is stable standard right now. By framework, I also mean a complete documentation and test scenarios, which will help you to help the developers to plug your platform systems into our test suite. And most of all, we plan to provide our platform online for the community. Let's have a quick look at the architecture, high-level architecture. We have the blue boxes on the left-hand side. These are test runners with NSI reference implementations. We have mock network resource manager underneath. All of them form some kind of topology. And we allow the user to plug its own NSI implementation into this topology. So he can log into the portal, provide all the information required to plug his implementation in the system, and execute a test against the suite. So what can be tested? First, we focus on the basic things, message testing. So we check the syntax, we check semantics of the message. We also record all the message flows. And this has been already implemented. We also test workflows. So we create custom test cases. We provide a set of templates which are available on the website, so the user may just select number of tests to be executed against his stack, and he runs these tests. And there are two other items which are under discussion at the moment. Pathfinding simulation, which is mainly for aggregators. So if we are going to check if aggregators are capable of calculating properly multi-domain paths. And basic stress tests. So we also plan, we have a discussion internally, if we can run a performance test against different implementations. So we can compare the performance of these implementations. There are several problems behind this. So each platform may run on a different hardware platform, different RAM, CPU. Also network conditions may affect these tests. So there are a number of discussions, there are a number of issues to be solved. So how to run tests in our system? First, the user needs to register in a portal and log into the portal. Then he selects tests from predefined templates. he needs to configure all these test cases. So we need to know, from the platform point of view, we need to know what are the URLs of the remote platforms and how to establish communication between our systems. Then we start tests. We distinguish manual and automated tests. So automated tests are these which we can handle and initiate automatically from the system. So I'm going to explain this later on. So part of the tests can be done just by clicking the portal. And the portal, the system behind, will contact proper instance of the NSI implementation and perform testing. While some of them, we call them manual tests, will require user intervention. So if you have an Eclipse platform, an example, you develop your software in Java, probably you will need to add a unit test. So you run your test, providing a first, let's say, step to the whole workflow. I will explain this in a minute. And then all the test results are stored in the CTS portal. So in the standard, according to the standard, there are two major roles of the system under test of the NSI implementation. It may either play a role of requester or provider. But there is also a special role, which is aggregator, and then it appears when the system has more than one child. And it has a responsibility of aggregating the responses from each child. So now I'm going to explain you how we plan to handle these situations. So the first, requester role. So this is the situation where the system, NSI system under test, needs to initiate tests. So it sends several messages to the reference implementation, and first what we do, we validate request message formatting. So this is the first test we do. The second responsibility of the reference implementation is validation of sequence and content of received message. So it must be compliant with the NSI state machine. Then we need to generate properly events and messages which are sent back to the system under test. And again, it must be compatible with the state machine. Last but not least, our reference implementation, if needed, may hide the availability of other platforms which are hidden behind our reference implementation. So in this way, we are responsible for generating proper messages, and our NSI reference implementation may look like a system which hides the availability of other domains on the path. The second role we need to test is the provider role. So here, this is the, let's say, what I called automated test. So now, this is the platform initiates the test and sends messages to the NSI system under test. So first, we need to generate these request messages to be sent towards the system under test. Once we receive messages from the system under test, we need to validate the received message, the syntax, and we need to generate properly events and messages to be sent towards as a response. And then we need to also check the messages if they are compatible with the NSI state machine. And last but not least, this is the positioning of the system under test if you are going to test the aggregator role. So as you see, we have more complex topology here. So your system, the system of software developers, is plugged in the middle between the requester agent and provider agents. So the system will act as a platform in the middle of the whole chain of processing. Okay, let me give you a couple of screenshots from what we have done already. So this is the portal. We demonstrated this a couple of weeks ago. So in this portal, you need to create a project, And this corresponds to the single user NSI instance. So you register your implementation, provide all necessary information. Then you need to position yourself in a topology. So you are able to download the topology file from the portal. And again, you need to provide your internal topology to the system. So we have the same state of all agents in the whole topology. You need to provide. You need to define test cases, and these test cases can be derived from templates, which are predefined, reusable definition of single test scenario. So how the test scenario may look like? This is an example of a test scenario. So in this test scenario, we have 5 operations. We'll test 5 operations, and you will see on the screen which operation failed according to the standard, NSI B.0 standard. And this is an example of an internal message we exchange in a system. It's an XML-based language. This is how we define test cases for our platform. So in this XML, we need to include all information required to configure properly all NSI reference implementations, instances in a system. So we need to have all endpoints registered, all URLs, and also we need to have a set of operations which we are going to handle in a single test scenario. And here you see an example of the request of the reserve message. So we expect that the system will validate if all the information included here in this XML are valid. This project is not only for doing the project, but this project is for the community. In fact, we need users which will test if the platform we provide is good enough for them. So we, let's say, started some public consultations, and we tried to capture community requirements. So we had several presentations of this project already, and we had also the first proof of concept demonstration, which was given early September. And we tried to collect all this feedback and analyze this in order to provide a better platform for the community. So just to give you a couple of examples, 90% of difficulties come from testing data plane. And this is true. When you deploy your platform, you have your real network underneath. So it's important that our platform will be capable of, in our platform you can configure mocks, network resource managers, so they simulate real-life circumstances, so they generate events, errors, leak problems properly, and then we may test the platform in close to real-life network conditions. The second thing is the standard may say in several places that the NSI implementation may either ignore or send failure messages. So it's up to the developer to decide how you plan to run your implementation. So you have a bit of flexibility. Then it's a problem, because then it's a problem how to test it. So our system is, we plan to have our system fully, let's say, responsive as possible, but also configurable as possible. So you may add features which you expect to happen in specific operations. In example, you may expect failure message to be sent, not just ignore. And this is going to be configurable from the portal. And last requirement, there was a request for having this project open to public, hosted on GitHub or elsewhere. Yes, we plan to open the whole platform as soon as possible. We are not stable enough yet to open it to the community, but we plan to do this soon. Hopefully by the end of this year, this project will be available as an open source, so the community may help us to build a better testing platform. Okay, just to summarize, this project is to provide support for developers. So we provide a reference implementation of the NSI standard protocol. The problem is that we are not going to claim that this is the implementation, so everyone should check against this. The plan is to have it, let's say, more, implemented in more interactive way. So if there are requirements from the community to change things, we are happy to handle this. The good thing is that it may provide early feedback for integration and system test. So as long as you are developing the system, once you plug this into the platform, you may continuously test features. The isolation, customization, and the repeatability of tests, this is important. So once you define your test cases, you may run this. If you change something in your code, you may run these tests continuously all the time. And we believe that this reduces efforts, especially for testing existing implementations, which are plenty. There are many of these implementations nowadays in the market. Yes, as I said, we have, there is the interpretation of the standard may be not clear, and we are here to also to listen to your discussions, to provide some help if needed, or just to get your suggestions into account. Last but not least, this is going to be an online platform available for everyone for use. So, thank you very much.
So we have time for a couple of questions. Okay.
Yes, so I was very pleased to see that you're making this available as an open source for future support. And I guess your funding is coming through the Open Core project, which comes to an end in
End of March.
Next year. So what I would like to see, and I think it's perhaps a question for everybody here, is how we can continue to fund this as a service to support NSI developments and NSI compatibility between implementations. And so I don't know, has there been any offers within GN4 to support this, and how can it be supported by the community?
Thank you for this question. Yes, this is important. As usually, the development project ends and then the product is available. So the question is how to maintain it, how to provide further updates. I'm in a discussion with activity leaders of GN4, and I will try to secure a bit of minimum funding for having this platform online during the lifetime of GN4.
Related to that, one small question, because the way this project has come about has been through this new project called OpenCore, where Kian is soliciting. It's a small add-on project with outside partners, typically with industry partners. So I'd like to, if you could just say a few words about how that works. Is that something you think is beneficial for the Kian project, or is it just another complication?
From my point of view, I will explain my personal point of view on this. I think it's a great idea. It's an opportunity to have a fresh blood in this community with good ideas. I'm referring here to the partner we have in the project, a small SME, which is a representative of industry. So they provide know-how on control plane developments. So it's beneficial for the community. Such a collaboration. So I believe in my view, it should continue in GN4.
Okay, in the future. Thank you very much. And the last speaker of the day, Johan George. Okay. Johan owns a master's degree in network engineering from the Technical University, and has spent a couple of years now at Nordinet,
PhD student doing a PhD in optical engineering. And I spent a good bit of that time with our solution, the fellow labs facility in Paris, where he in particular has been looking into elastic optical networks. He will be talking to us about some of the technologies that might help us address some of the questions that it proposed to us originally. Questions about how to achieve scaling and how to achieve the evolutionary change that is necessary to cope not just with growing bandwidth and usage requirement, but also with the high levels of energy consumption and the cost of power for
Thank you for the introduction. So my name is Joan Turus, and I'm going to present the work that I've been focusing on during the last 6 months to counteract the over-provisioning and the inefficient use of optoelectronic resources by deploying some energy-efficient strategies in optical networks, and here is a use case for NRAX. So the outline of this talk will start with an introduction on the energy efficiency things, then a proposed traffic model based on data from NordNet, then a few details on the energy reduction strategies, the control plane implementation, and some results. So already stated from 2007 by a Gartner report, the ICT industry accounts for 2% global CO2 emissions, which is a figure equivalent to aviation. And this report also drove the first studies about energy efficiency in optical networks. Moreover, another report shows that in Germany, the demand of electricity from the ICT industry is about 11% from the overall electricity consumption. And currently, ITU states also that between 2 and 3% of global greenhouse emissions are assigned to the ICT industry. And another reason for focusing on this increasing growth of electricity demand is the fact that, as shown by Cisco in the VNI reports, between 2013 and 2018, the overall global traffic experienced a growth of 3 times. And we can see that the classical file sharing, web data, and managed IP videos, they lose their percentage between these 5 years, while the internet video traffic grows 50%. So it's going to be the main driver of deploying core optical networks. Moreover, most of the studies focus on the reduction of the CO2 emissions, but there is another limitation given by the amount of the electricity that can be generated in the world. And if we consider that the amount of energy consumption follows proportionally the traffic, we can already foresee a bottleneck in less than 10 years because of this. And however, this consumption can be decreased by advances in the silica technology, but this is still not low enough as what it should be reliable for the ICT industry for growth in energy consumption. So we want to make use on the traffic fluctuations and growth experienced in these core optical networks, and we take the case of NordNet. And here we have the statistics of the NordNet traffic with customers in week 23, I think. And we can observe these strong day-night fluctuations and the weekend drops. Moreover, we can observe 60% traffic growth, and both these two aspects enable a strong over-provisioning, and in return, the over-provisioning makes a very inefficient use of both optical resources and energy consumption. So based on this data from NordNet, we created our own traffic model, which the model takes the NordNet data and averages it and samples it with 1 hour so that we get the day-night fluctuations, and then the weekend drops. And then we get the weekly pattern that we multiply it over 1 year for 48 weeks, and then we add a growth of 60% on the peaks and 30% of the bottoms, and also add the specific academic backgrounds like drops during Easter, summer holiday, and Christmas. So having this traffic pattern, we looked into the possible ways of reducing the energy at the optical layer, and one way is to apply sleep mode approaches for the optoelectronic devices. And by optoelectronic devices, I'm referring to transponders and regenerators. And in this case, the regenerators are using an architecture of back-to-back transponder configuration. So taking the 100G PDM QPSK transponder, the measured power consumption for this is 350 watts for on and only 8 watts for idle mode, and of course 0 for off. And the big advantage of having the idle mode is that when the transponder or regenerator is not used, instead of placing it in off mode, keeping it in idle allows a fast switch to mode on, because we don't turn off the laser completely. And then the power of the regenerator, because of being a back-to-back transponder, is just the double of the transponder. So this is with the sleep mode. While the other approach is to use the so-called data rate adaptation. And in the static elastic optical network project, together with Alcatel, there was a proof of concept elastic transponder and regenerator, which was able to tune its data rate between 25, 50, 75, and 100 gigabits per second. And the way these data rates were achieved was by varying either the symbol rate or the modulation format. And an interesting fact on the data rate adaptation is that when we keep the modulation format fixed for choosing different data rates, we always keep fixed the reach of the transponder, obviously. But when we vary the baud rate within the transponder, we always vary the power consumption, which is not the case when we vary the modulation format. So, important note here, by varying the symbol rate, we vary the power consumption in that transponder, while varying the modulation format, we vary the reach. So, taking these two approaches into account, we can create 3 energy saving strategies, and one of them is called modulation format adaptation. And we can take this example of a 100 gigabits per second channel between this source node and the destination node passing via this regenerator. And if during the day this 100G is configured with the PDM QPSK modulation, because of the limited reach it needs to pass by this regenerator, and in total it consumes 1400 watts. But if during the night this decreases to 50 gigabits per second, what we can do is to change the modulation inside all these optoelectronic devices from PDM QPSK to PDM PPSK. And that one allows for a longer reach, and thus we can bypass this regenerator and place it in idle or in off mode. And then the overall power is half, only 700 watts during the night. While the other approach is to do symbol rate adaptation, and by symbol rate adaptation in the same scenario, if during the night we drop to 50 gigabits per second, what is going to happen is that in all the 3 optoelectronic devices, we decrease the baud rate from 28 to 14 gigabaud. So then we reach 50 gigabits per second, and all the optoelectronic devices consume now a much lower power, 206 and 412 watts. And then allowing in total with this adaptation to have 824 watts during the night. And then the third approach is to always choose the optimum adaptation between the two, and in this case would be modulation format. So having these 3 energy reduction strategies, we wanted to deploy them in the network by making use of a GMPLS distributed control plane. And then we had automatic node reconfiguration with RSVPTE, and we needed to use a policy controller in every node to decide on reconfiguration or, if needed, recovery, and to provide the necessary information to RSVPTE to perform the signaling along the path. So this one was a simple implementation. And then we took two network scenarios. One was Giant with a large footprint and Nordonet, smaller footprint compared to Giant, and we demanded 3 types of connections depending on the peak capacity, being 50, 75, and 100 gigabits per second. We wanted to study also very dynamic environment of setting up connections, so we had inter-arrival time between them of 1.6 hours and halting times of about 38 hours, resulting in 24 airlines generated in every node. And every link here was configured with DWDM 80 wavelengths. So the 4 scenarios investigated was the classical one, where independent on what's coming in the input of the channel, we configure a fixed 100G with PDM QPSK and 28 link baud. And then in the second scenario, we try to adapt the modulation format while always keep fixed the 28 gig baud. In the third one, we keep fixed the PDM QPSK, the complex modulation format, and adapt the symbol rate. And the fourth one is the mix, where we take the optimum choice between the 2 adaptations. So the interesting part of the results was to see during 1 year of simulated time the overall power consumption. This one is for Nordonet network, and the blue line shows the power when all the channels are set up with fixed 100G. So it stays relatively constant to 250 kilowatts. And then a zoom over week 42, where we can see easier that by applying modulation format adaptation, the power can be much more lowered, and it starts following these day-night fluctuations and then drops a little bit more during the weekend. Similarly for the symbol rate, and much more for the mixed adaptation. And here we were able to decrease it with modulation format adaptation by turning off or to idle some of the regenerators, while in the symbol rate, none of this sleep mode was applied, but only retuning the symbol rate in all the transponders and the regenerators. Similarly, for Giant, the power for fixed connections is much higher, more than twice, because there are more nodes and usually the links are longer, so they have more regenerators. And the difference compared to the Nordonet case is the fact that here the modulation format adaptation, the red curve, it goes lower than the symbol rate one. So we are able to provide much higher energy savings by taking off some of the regenerators or putting them into idle compared to just retuning the symbol rate. And in order to assess these savings, we computed peak to average rate to see what is the theoretical saving in case the power would follow exactly the traffic pattern that we have in our model. So in case this would only account for the day-night variations, we could have ideally 32% power savings. But in case this model would account also for the weekend drops compared to the rest of the days, we could add an extra 11% savings. And in case of taking the overall growth and the over-provisioning during 1 year, that allows for an extra 26% savings in both networks. So reaching in total, ideally 69% energy savings during 1 year. And then the measured values for this implementation in Nordonet and Giant shows that for mixed adaptation, the optimum one, we can reach around 49% for Nordonet and 50% for Giant, which is relatively close to the 69 ideal one. But still there is this gap because the transponder and the regenerator can only tune between 4 data rates and not a higher tuning degree. Then we can see that the modulation format adaptation performs much better for Giant than for Nordonet. And the reason for that is that Giant, being a large footprint network, it demands in average much more regenerators for every path, and that allows better play with turning off or idle those regenerators, which is not the case for Nordonet. And on the other side, symbol rate adaptation is relatively the same, provides the same savings, and it's better maybe to be used in small networks like Nordonet one, because it allows a simpler control plane or a simple GBRS implementation, since we don't need to turn off or idle any optoelectronic device. So So this being the final results, concluding the things, we have this well-known and observed traffic increase, which always turns into over-provisioning, and the over-provisioning determines a strong increase of the power consumption. And then we need to make use of these periodical and predictable traffic variations in the core networks, and by having this opportunity, we deploy energy-saving strategies based on sleep mode of electronic devices and data rate adaptation with modulation format, symbol rate, and the combination of the two. And then practically, or at least from the simulation results, we could achieve 50% energy savings, which turns into operational OPEX savings for both NordNet and Giant topologies. And modulation format outperforms symbol rate adaptation in large footprint networks, like the Giant in the current study. And symbol rate adaptation is preferred when the networks are smaller or when they don't use regenerators, because it allows a less complex signaling. So this was all the observation. Thank you.
Any questions? Since part of the study is on my network, an obvious question is, how realistic is it that we're going to see these types of technologies in the actual equipment that we're going to be able to buy in the next part of procurement? Are we actually going to realize these things? I think these are, for the Xiaomi, there's a 50% saving towards a budget of 800 kilowatt, right?
Yes.
Constant usage, but these are not, it's not just turning off the lights, it's really substantial power savings. So where are we with actually having this kind of technology available in standard platforms?
Yes, so one thing is the transponders and the regenerators. These elastic proof of concept, they are available in the market. They should be at the same price with the 100G current transponders, but it's still a matter of operators willing or not to provide this increased complexity in the control plane and deploy these flexibilities. But on the other side, it should be a way to start provisioning the power in our network, not via breakers, but by paying it per time. So paying cheaper energy during night and even turning off some of the sources. And this is not the case yet, at least not for our network.
But in theory, it's a matter of an operator balancing the cost of this slightly more complex technology versus the power savings that and the cost savings from that. At some point, there will be a break-even. Do you see that break-even coming within the next 5 years?
Personally, not really. I think it's still more a research issue because whatever new needs to enter in an operating environment, it always hits the question, does it going to add another complexity to the network? And if the answer is yes, it normally goes with a no answer.
Okay. Thanks a lot. Other questions? Yeah. Chin. Okay.
So I just had a question on, do you have a sense on how long it takes for the, when you switch from, say, PSK to BPSK, you switch a regen off, right? How long does it take for it to rebalance the wave and have that wave up and functioning?
Yes, the laser is not going to change. It is, from what I remember in the transponder implementation, it was a matter of DSP configuration, and there were some nanoseconds reconfiguration time.
So I'm assuming if you switch the regen off, that your launch power and stuff, right, you have to rebalance your launch power because you're bypassing the regen, right?
Yes.
Now I'm just wondering, in cases like this, is that, so what you're thinking is it's just going to be a matter of milliseconds for it to actually kind of set itself up and you're good? Is that what you're thinking?
Okay, I didn't hear the question.
So if you actually switch the regen off, right, and now you actually pass through the wavelength, right, your launch power potentially may have to be different, right, because it has to go
Yes.
How long do you see that actually taking place in the system?
In the simulations that I've seen Bell Labs doing, whenever they were tuning the modulation format, they used the same power, the same output power.
Okay.
So it was just a difference in reach, but they were not tuning that power, the output power.
Okay. More questions? That's not the case. So thanks again, George.